to all this Department of Mathematics and IQAC, Maulana Azad College, is organizing a seminar, a webinar, Recent Trends in Mathematics and its Application in this Pandemic Situation. On behalf of the Department of Mathematics, I, Dr. Babli Shaha, Associate Professor, like to thank to our principal, Dr. Shubhashish Dotto, for his continuous support to hold this webinar. Unfortunately, he cannot attend this webinar due to some unforeseen circumstances. Now I request Professor Subir Dasgupta, the coordinator of IQAC, to inaugurate this webinar. Sir, please.
Thank you, respected principal. Our two learned speakers, Professor Malay Banerjee from IIT Kanpur and Dr. Shuikat Majumdar, IIT Bombay, Head of the Department of Mathematics, Maulana Azad College, all my colleagues and my dear students. On behalf of Principal Maulana Azad College and as IQAC coordinator, I welcome all of you to today's national webinar on recent trends in mathematics and its application, which is jointly organized by Department of Mathematics and IQAC Maulana Azad College. On behalf of the college and IQAC, I express my sincere thanks and gratitude to our honorable speakers. I hope these two lectures will enlighten many important insights of mathematics, and our students will acquire more knowledge about that. I wish all the best of today's webinar. Thank you.
Thank you, sir, for your valuable speech. Next, I request to Dr. Kartik Chandra Basak, Head of the Department of Mathematics, to give a welcome address and to deliver a speech about the webinar. Sir, please.
Good afternoon, everybody. I hope all of you are safe and in good health. First of all, I like to thank our principal and IQAC coordinator for their continuous support for organizing this webinar smoothly. I heartily welcome all the speakers, faculties, research scholars, students for this webinar. In this present pandemic situation, the department has organized their webinar to encourage the undergraduate students for gathering knowledge about recent trends in mathematics as well as its application in real life. I think such type of webinar helps them to choose specific branch of mathematics in their higher studies. Finally, I wish a grand success of this webinar. Thanks to all attending this webinar. Thank you.
Thank you, sir, for your valuable speech. Now I request Dr. Somnath Bandopadhyay, Associate Professor of the Department of Mathematics, to introduce our first speaker, Dr. Shuikat Majumdar.
So, good afternoon, everybody. Thank you, Professor Shaha. So, it is my privilege to introduce Dr. Shuikat Majumdar. Mr. Majumdar completed MSc in Mathematics from TIFR Bangalore, completed his PhD from Lorraine Institute, Elie Carton, France in 2016. I don't know what is the actual pronunciation in French. So, okay. As a postdoctoral fellow, he spent at University of British Columbia and McGill University, Canada. At present, he is professor of mathematics at IIT Bombay. The main area of his interest is partial differential equation that occurs from differential geometry. Professor Majumdar published his papers in esteemed journals like Advanced Nonlinear Studies, Communication on Pure and Applied Analysis, Journal of Differential Equation, etc. Today's topics: an invitation to calculus of variation. So most of our participants are undergraduate students. So I think Professor Majumdar is aware of their limitations. So please, Dr. Majumdar.
So thank you so much for the very nice introduction. Okay, so because it's a pandemic and I'm doing it online, so if there are some technical issues, if my voice is not coming properly, okay, or if my video stops, please let me know. Okay, so thank you for this very kind invitation. Okay, I think it's a great opportunity for both students and for me to this platform presents a great opportunity for all of us. Okay, I'll try to present one area of mathematics which I roughly work upon. Okay, and hopefully this will be helpful to our students. And this will be an introductory talk. So if you have any questions, any doubts, please do not hesitate. Okay, I will write my talk so that you can see. I'll start my picture. So let me start with that. Okay. So anytime if there is any doubt, please do not hesitate. So can you see my screen? No? Okay, I think I also can see the screen. No, I will try it once more. Share screen. Yes, now it will start. Okay.
Yeah.
Okay.
Okay.
Okay. So we'll start now. So again, so if you have any questions, any doubt, please do not hesitate. So I'll try to, because we cannot communicate to each other directly, this is through online. So please let me know. So, okay, so what is the subject? So we'll start with this, a very old subject and a very fundamental subject in mathematics. It's called the calculus of variation. So maybe that's not the best thing. So it's a very, very old subject, and it's a very still active area of research. It's a very living subject. So there are a lot of difficult problems. There are a lot of interesting problems still in this area. Yes, I will start with a few examples. Okay, I will give a very rough overview, and I will not be very mathematically rigorous. So we'll just see some useful examples. Okay, so basically the thing is we want to find. So if my handwriting is not okay, if you don't understand, please let me know. So want to find the best shape, or I'll write the best, not shape, the best form, or the optimal form. So we'll see what it means like. So the one of the tasks of calculus of variation of this whole subject is to find the best possible thing. So how do we choose this best possible thing, and what are these best possible things? Okay. So let me start by one very simple example. So this will describe, is coming from describing geometric or physical quantity. So I'm very vague here. So let me first start with example. So example number 1. So geodesics. Okay. So the geodesics is a very old problem. So what we want to find is that given 2 points. So suppose you're given 2 points in space, and you want to find the path which connects these 2 points and which has the minimum possible length. Okay. So now we all know the solution to this problem. It's a straight line. Okay, so maybe we'll draw some pictures. So therefore, I wanted to write so that I can draw some pictures. So let's suppose I have this point A alpha and another point B beta, and I want to find the path which minimizes the distance between them, right? So it can be a path like this, it can be a path like this, but we know the path is really a straight line, right? So how can we say that it's a straight line? So it looks a very stupid problem, right? But it's a very, very deep problem. And the more we look into it, we'll see that there are more issues to discuss. So given 2 points, let me, for simplicity, we take it in R2. So in the plane, okay, and B beta in the plane, okay. And now you want to find, the question is, find the curve, okay, of shortest length. Connecting these 2 points. All right. So the question I will pose here is, the remark I will write is, we know the answer is a straight line. We should better think that why the answer is a straight line. Why the answer is a straight line. Why not a line which is curving like this? So why straight line is better? So we'll try to answer this question. Okay. So how does one see this fact, okay, mathematically? Or maybe I'll just write like this. Okay, so let's kind of mathematically formulate this problem and then try to kind of pose this problem in a rigorous way, and then tell you about the answer and why this should be this straight line. Okay, so first of all, we know the distance between the points. So I'll very quickly write D. Okay, the distance between these points is, so the old Pythagoras theorem tells us that it's a beta minus alpha whole square plus b minus a whole square and square root of this. Okay, so we have to derive that this is indeed the case. Okay, and I'll also write the equation of the straight line connecting these 2 points is given by y is equal to, so here we have that this is the slope is given by beta minus b, and then we have alpha minus, so am I doing it right? So okay, beta minus alpha and b minus a x plus, so like this, and then a. All right. So how do we derive that this is really the case that this straight line minimizes the length? So first, let me define the length. So we are going to be kind of very vague. So this talk is just for the, we'll not define everything from ground below. We'll take a definition, and then there are many ways to make this definition better. There are many ways to generalize this definition and expand this definition. Okay. So just let me give you one definition of the length. So we'll consider the curve connecting these 2 points as a point gamma, as a curve gamma. So consider, so I will maybe write it like this: the length of the curve gamma. So gamma is a function of, so gamma is more like, so maybe this is for notation, so please I'm not very rigorous here. So gamma is more like y is equal to gamma is a function of x. Okay. So length of the curve connecting. So joining these 2 points is given by the arc length formula. So this is the integral given by the arc length integral. So I write the length of the curve gamma joining from A to B, and then I have the distance. So therefore, you see the square root 1 plus the derivative of gamma, okay, and then dx. Okay, so this is the length of the curve gamma. So we have extra constraint that with gamma, so this is a curve. So it starts at the point. So when x is equal to a, this is where is equal to alpha, and when my x is equal to b, this is equal to, this is at the point, the curve is at the point beta. So the length of the curve is given by this formula. Okay. So I've written a formula. This formula is very, so these type of formula is going to be crucial for us. So, okay, again, if you don't know how to derive this is very simple. So what you do in the calculus, yeah, you approximate it in a small part, rectangular part, and then this is basically x coordinate, and this is how you move around the y direction, and so therefore the hypotenuse is given by this. Oh, so I forgot the square. So and you integrate it, you sum it over all the small lengths from A to B, and the usual Riemann integral trick. You make a division smaller and smaller. So from the sum you get some integral, and this is how you get the formula. Okay, so immediately one thing that you can see is that if you calculate, so let me write gamma, the straight line. So this denotes a straight line connecting the points A alpha and B beta. Then the length of the straight line you can immediately calculate is equal to this. So this is very simple. So gamma prime for this straight line is just equal to this quantity. The other part vanishes. So you replace and substitute this. So you have B minus A whole square in the denominator. You take the square root. So that makes it B minus A, and you integrate it from A to B. So B minus A will in the denominator will kind of cancel. So this is really indeed the length. So beta minus alpha square plus b minus a square. So you can really see that this the straight line is achieving the minimum length, right? So the question is, can there be any other curve having, so this is the length having the minimum length, right? So the length, this is the minimum length because this is the distance between these 2 points. So whatever is the length of the curve joining these 2 points, it has to be at least this, right? And the straight line, you can just substitute the equation of the straight line into the formula for the length, and you get immediately like this. So you do get that the straight line minimizes this, but this is you're usually doing it from the classical geometry. You're not using any calculus fact. So we want to establish this in a more rigorous way, in a more from the viewpoint of calculus. Okay, and also you can ask, are there any curves which can attain this particular length? So I can complicate this problem. So instead of just we have this set up in a plane, so we can have it in higher dimension space. The same thing will work. So we just will have more coordinates. That's all. So that very much is understandable. But the more complicated thing, what about this problem, same problem? So instead of doing it on a flat space like a plane or Rn or an Euclidean space, you do it on a curved space. What about the same question on a curved surface, right? So if I give you a surface, if I give you a sphere, I can ask the same question. So given 2 points, P, let's say P and Q on a surface. So on a surface S, how does one find the curve of shortest length? Shortest length joining them. Okay. So for example, if I give you a surface like this, so I give you P, I give you Q. So how can you find the curve of the shortest length? Okay. So if I give you something like this, a torus, I give you a point here, I give you a point here. So how does one find the shortest length? Does it go like this, or does it go along this curve? Okay. So there are some examples on the sphere. If you take on the sphere, okay, on spheres, so on the surface of the ball, the geodesics are given by great circles. Okay, so basically you take the this is more like doing geography. Okay, so you look at the latitudes or the longitudes, I forget sometimes what is what, from on the spheres. And so if you have 2 points P and Q, this is part of this circle, like a slice of the circle on the sphere. Always. So this is not an abstract question. This is very important for practical purposes. In aviation, in navigation, this is very important. So all planes always try to fly in a path that minimizes the length. Okay? But this question is highly non-trivial, and the way we have not solved it. The way we can intuitively guess the solution in the Euclidean case is not going to work. So if you have a cylinder, so then the geodesics can be straight lines, the geodesics can be circles, or it can be something like this. So there are 3 candidates for geodesics. So this is so you can have numerous kinds of geodesics. Okay, so you have to be very careful. So in what way can one systematically solve this problem of finding geodesics? Okay, so okay, this was the first example. The next example is something very classical again, and very much related. You just have to introduce a factor, but it comes from physics. So next is geometric optics. So this is the Fermat principle. So again, if you have 2 points, okay, again denoted by P and Q. Let me again write the same notation, P and Q. And the light is traveling between these 2 points. Light is traveling between these 2 points. But the catch here is that the density of the medium, light travels in a medium, light is traveling in air, light is traveling in water or whatever. It's traveling through a medium, but the density of the medium is not uniform. It's an inhomogeneous medium, but we as mathematicians don't care about it. So we just say that the density is a function like C of, or maybe we'll write G of X and Y. So this is the density function or refractive index, whatever is the right physical notion. Okay, so and the light is traveling between these 2 points, P and Q, in a medium. The density of the medium is non-uniform. This is very important. Okay, so how what is the path that the light can take? Okay, so is it a straight line? That should be our first guess. The answer is no. Okay, we have the phenomena of refraction, therefore, and this could be counterintuitive because we'll see why this is the case. the answer cannot be a straight line in general. The answer can be, depending on the medium, the answer can be any kind of curve. Okay, so this is, and the way this was first, one of the person who first recognized this was in 16th century, 17th century Fermat. So this is called the Fermat principle of least action or least time. So it tells that, so the important point is least, the important word here is the least time. I'll also write the word action. So what it tells us that the light will travel in such a way, this is a very fundamental kind of physical intuition into these kind of problems. I'll not debate whether in nature things work like this, but from the mathematical viewpoint, it's a very important tool to look at our problems. So it says that light will travel from point P to point Q in such a way that the total time taken is minimized. It does not care if it wants to go in a straight line. If it goes in a straight line, and suppose if it goes in a straight line, the density is more at that point. So it will not travel in a straight line. So light somehow detects all the possible paths that it can travel, and it will choose the path for which it will take the smallest possible time. So I find this idea very fascinating, and this is the heart of the calculus of variation. And in fact, Fermat is considered one of the fathers of the subject of calculus of variation. Okay, so Fermat's principle of least time is the light will travel. Okay, so light will travel in a path such that, so again the question is, we want to find the path. The unknown is the path, such that the total time taken, so handwriting is very bad, time taken is minimized. Okay, so this is a very fundamental thing that Fermat recognized. Maybe many other people before him also recognized, but it's usually attributed to Pierre de Fermat. Okay, so this is the same Fermat for whom we have the famous problem in number 3, the Fermat last problem. Okay, so how does one mathematically formulate this problem again? So you have to, this can be written as some, in an integration form. You want to find the curve gamma. So I write the same like L. So if you recall what we wrote in a previous formula, so it's the same thing, but just an extra factor, which kind of indicates the fact that the medium is inhomogeneous. Okay, so Gxy, Gx, sorry, gamma. So if you look at it a little bit closely, you'll see that this thing, so if you change if you take a different part, let's say gamma 2, so this quantity G on gamma 2 is different. So this is where the effect of the medium is coming, and this is kind of very amazing kind of fact that the light kind of, before even it starts traveling, it senses all the possible direction it can go, and it only goes in the direction it knows it will take the minimum time. So this was exploited later by in 1950s, 60s by Feynman to formulate in the language, not in the language, but in the same ideas of calculus of variation, the quantum mechanics. All right. So you can, I will not again get into the physical derivation of these kind of problems. So it's kind of complicated and it's not useful for us, and also I'll not explain very nicely. So again, the question is, we want to find a gamma for which this kind of, we want to minimize this length. So again, the main point here is that, as in the first example, we want to find something, a gamma, where we have infinitely many choices, right? So gamma, between 2 points, there are infinitely many curves. One curve can go to moon and come back, and one can just travel in a straight line. So we don't know, but the light chooses that particular gamma, which minimizes this integration formula. Okay. Okay, so next thing, let me see what I have. So this is called the, and you can derive by this Fermat's principle, you can derive all the laws in geometric optics, laws of reflection, refraction, lens, design, everything. Okay. Okay, so let me kind of give one more example. So how much time has gone? Yeah. So let me move to the next couple of examples. Okay. So I will not describe too much geodesics on curved surfaces. I will next move to something very fascinating, and which is a very, very rich subject. In fact, the first Fields Medal in mathematics was given for work in this area. It's called the minimal surfaces. So it's like a higher order generalization of the geodesic problem. So geodesic, what do you say? You have 2 points. You fix 2 points in your control. You have 2 points in your control, and you want to find the curve which joins these 2 points and which has the minimum length. So in higher dimension, so I give you a curve, a simple closed curve or the Jordan curve. So given a simple closed curve, so gamma. So please don't be perturbed by my notations. So this is some curve gamma. Okay. So now I have some gamma fixed. Okay. And now you want to gamma in. This is very important that I should mention. That this is the main reason that the problem can be very complicated in R3. Let's see. So in the space, I take a curve. Okay. So the curve can be anything. It can be the circle, the boundary circle. It can be a twisted circle. It can be like a helix kind of thing. It can be many, many complicated things. Okay. So how it twists in space, that creates the main problem. One of the main problems. Okay. The question is, find a surface or find, okay, I'll write a surface, even if, because there can be more than one, in general, more than one surfaces having the same minimum length. Find a surface S, okay, such that, okay, I'll not use my notation of such that, with or having boundary gamma. So you have the boundary gamma and you're fitting. So imagine that you have a string or you have a wire, okay, and you're fitting a piece of cloth on the top of that. Okay, I will give why it is minimal surface. I'll give you a very important example, just in a couple of lines. So you want to fit it in such a way that the area is minimum. Suppose you want to stitch something and you have a boundary and you want to put a piece of cloth on that, and obviously you want to put it in such a way that it's a minimum area, right? So this is the minimum surface. So having boundary gamma such that the area of S is minimum among all surfaces, all possible surfaces having gamma as its boundary. I hope I'm able to explain this problem. So you have this boundary curve gamma, a simple closed curve. Simple closed curve, don't worry too much about it. It's just like a circle, but it has been stretched full, something like it does not intersect with it. So that's the only thing. So it's a simple closed curve and it's closed, like it's not a free curve. It's a closed curve, and you want to put a surface such that the boundary of the surface is this given curve to you. So earlier we were given the point, so now you're given the boundary. So now you want to fit the surface S such that you can calculate the area of the surface. So surface S1, you can calculate the area. Surface S2, you can calculate its area. So you want to find that particular surface whose area is the minimum. Okay, therefore, it's called a minimal surface. So maybe, okay, I'll not try to draw it on the issues. Okay, so maybe I can formulate this problem like this. So the problem is minimize your area of S. So this is an area, so we can write it as a double integration. Okay, if you don't know what it means, so don't worry, this is just the area, and you can very rigorously calculated such that the boundary of S is equal to the given curve gamma, given curve. Okay, so this is called the Plateau problem. As the Plateau problem. So let me tell you some history about this problem. So this was known a long time back, especially this was started by Lagrange. Okay, Plato was a physicist in 19th century France, and what he did was he used to do experiments with soap bubbles. So we all know, so you take a piece of wire and you used to dip it in the soap. So because of the surface tension, the bubble will will assume the form such that the area is minimum. So soap bubbles are examples of minimal surface. So whenever if you do a Google search about minimal surface, you'll see some very nice pictures of soap bubbles. Okay, but here the problem is, so if you have something in 3 dimension, if it's in 2 dimension, then it's obvious that it's the area that it's a 2-dimensional surface, so that the boundary is that curve. So it's just the area of that particular region. So if it was just in 2 dimensions, so imagine that this is in 2 dimension, then the surface is just a flat surface, right? So it's a however complicated the curve looks, if it is entirely lying in a plane, it could be some plane which is it need not be parallel, but some kind of plane, then this area is exactly, the minimal surface is exactly equal to the flat the flat surface spanning that particular curve. But if it is something twisted, okay, then it need not be, obviously it will not be the flat surface. So how do you find such kind of things? So this is called the Plateau problem. So the first Fields Medal was given for work in this direction in 1936 by Jesse Douglas, and later on Rado also worked. Okay. I'll write some names. So maybe this is try to draw a better picture like this, and the projection is like this. This is the projection. Okay. Again, you can formulate this problem. There are many ways to formulate this problem. So I'll just write one formulation. So you can formulate this problem as an integral formula. That is what we kind of seeking. So you can write this problem. As now minimizing the area. So earlier we wanted to minimize the length of a curve. Now we want to minimize the area of the surface S, and there are many ways to do it. This is called the non-parametric form. This is one way. If your surface is, so I'll just write my formula first. So again, this is like the distance of the y coordinate and z coordinate squared, and x coordinate is 1, so squared, and dx dy. Okay. If so, when S, the surface, is given as a graph of a function, is given as z is equal to u of x comma y. Okay, and then the boundary curve with boundary gamma given as some other function, let's call it u naught of x comma y. Okay. So you can always formulate these kind of problems in this particular way. So in fact, so you want to minimize this, and we have to give always a boundary condition, and this is the region. You can say that for x comma y in some region in the plane, Okay, so I'll write it maybe in the plane. So something like a ball over which it is defined, the surface. Okay. Then, and this is my, okay, I should have drawn a better boundary curve. This is my boundary curve gamma, and this is my surface S. And you have the further constraint. You have to have some constraint because remember, you cannot be a free surface. It's a surface that is constrained by its boundary gamma. So, and such that, so you have to minimize this A and minimize A such that the boundary U x comma y is equal to this boundary. Remember, this is exactly equal to the gamma boundary, okay, for x comma y in the boundary of my domain D. Okay. So this is one way to formulate this problem, but there is another way. So this was again solved long time back by Euler and others. It's if you want to find a minimum surface of revolution, you don't do so much complicated stuff. So you have some curve, okay, and you rotate this curve around this axis maybe, and then this is, let's say, y is equal to f of x. Okay, then you can write your a, okay, and then you can rotate this to give us get something symmetric. You can also consider the reflection around the lower axis. Then your two given surfaces are the top part and the bottom part, top half and the bottom half. Then you can write a very simple formula for this. Then first of all, my uxy is equal to a surface of revolution. So something like this, f of x sine of y. And then you can write this as integration from a to b, 1 plus, again, the derivative, this f of dx. So this exactly looks like what the same integral formula that appeared in the Fermat's principle. And it's very much, kind of very close to that. Okay, but here we have f prime and f, both something. Okay, but the answer here is very well known. So by a geometric intuition, we know what example of a minimal surface. If you forget about the boundary for a minute, so flat surfaces are minimal surfaces, as I told you. But one example of something non-flat is the is called the if you rotate this catenary, the catenoid, something like this. So it's a surface of revolution obtained by rotating the catenary. So this is one particular example, and you can get very pretty looking pictures, pretty pictures for this soap bubbles and minimal surfaces. And it's a very active area of research. People are discovering new things all the time. Okay, I will end with one last example. Okay, and then I will describe a little bit of general theory, and then we'll stop. So the last example is again a very classical problem. So maybe it's the most ancient of all the problems. So how many? This was number 3, hopefully, and this was number 4 then. Isoparametric inequality or isoparametric problem. So it tells you the following. Again, so the main theme of these problems, all these problems are, you have to minimize an object or you have to maximize. Minima and finding minimum and maximum are the same thing. You just replace the function with its minus. So you have to, or we say you have to find the extremums. You have to find the extremum values, minimum value or maximum value of these problems. Okay. So here the thing is that I give you a length. Suppose I give you a piece of string. So imagine I give you a piece of string, okay, and I ask you, okay, so you kind of arrange this string, you make a geometric figure, okay, so that you make a closed curve, and so and the area under this under this curve, okay, or the area which such that this curve is kind of bounding that particular area is the largest possible. Okay, so is the largest possible that one can get. So suppose I give you a string like this. So you can arrange the string like this. So I give you a string of length L. So given a length L, I can arrange it like this. I can arrange it like this on like a circle. I can arrange it like this. Okay. So every time the outer area, so sorry, the outer circumference length is always L. So you play with the string, you arrange it in any way possible. But the constraint here is that the total length is equal to L. So the length of the string is fixed. So, okay. So how do you do it in such a way that the area it encloses, the area inside the curve or the string, is the largest possible? Okay. So this is called the very ancient problem of Queen Dido, the Greek problem, 200 BCE. Okay, I'm sure there are analogs of this problem everywhere. So some queen gave a piece of string and told that, okay, whoever can enclose whatever area you can enclose, it's all yours. So somebody came up with a solution that if they enclose it in a way so that it's a circle, then the inside area is a disk, is like a ball, and then it's the maximum possible. But how do you prove it analytically, mathematically? It's a very, very, very important problem, and it's called the isoparametric problem. Okay, so let me kind of describe this problem. So suppose again S is a region. I say it's a region, but it can be again a surface kind of thing. It can be something which is not flat. And the whole thing can also be posed on. We live on a like a sphere kind of object. Okay, the Earth is more or less like a sphere, not exactly sphere. So we can kind of pose the same problem, right? And there is going to be difference because of the curvature. So suppose I give you a S region, better to say it as a region. Suppose there is a region S, and it's a bounded region. Is a bounded region with boundary. This is a traditional way to write the boundary, like a partial derivative. And there is also a reason for that. And the reason is one fact of calculus we all know is the integration by parts formula, which again plays a very, very crucial role in calculus of variation. So you have, this is the boundary. So for the time being, just it doesn't mean anything. It's a notation. It's a boundary. So suppose I give you a boundary del of S, then this tells us that then we write L of the boundary is the length. This is given to you, length of the boundary, and A of S is the area of S. So you have the same S, the S for the object S, you have its interior area and the outer circumference, right? So then the isoparametric inequality establishes the fact that circle is the best possible shape with respect to this. So you can the circle, if you draw any other shape other than a circle, it will enclose a small area. Then, so you can mathematically write this as length of this squared, okay, is always bigger than 4 pi area, 4 pi times area. So with equality, if and only if your S is a disk or like a ball or ball of some radius. Okay, so if it's a ball of radius, let's say R, let's say ball of radius R, so write it in brackets. R implies that A of S is equal to 4 pi R square, and length of this is equal to 2 pi R. So you can see the equality is achieved. And but this is very simple to verify. This is nothing new. But the main thing is that this is an if and only if. It is only an equality if this is like a ball. No other shape will assume this inequality. And for every other shape, this is bigger than equal to. So for every other shape which is not a sphere, this this inequality is strict. So if I give you a shape which is not a sphere, the length square is strictly bigger than 4 pi times its area. So this is a very, very crucial fact. Okay. So these are the examples I wanted to give. These are very classical examples, but very much also still now the driving force behind this subject. Okay. So now I will describe a little bit of, I'll write everything in one kind of formulation and give you what is the so-called Euler-Lagrange equation. And one Euler-Lagrange equation we all know, and this has a more fancy name because we have to deal it with higher dimension, in fact, infinite dimension. Okay, so the question, everything that we have done so far, we can write it like this. So minimize. You have to minimize something, right? Every time we had an integration formula. So minimize, we can write it like this, maybe L. L is something which is given to you, which can be a function of X, the function itself, and the derivative of the function. Okay. And all these are itself depending upon X dx. So maybe I will write, so it's more evident that these are also functions of X. Okay. So minimize this. So minimize. So here we are finding a minimum. So it's a very simple thing we all learn, that given a function, find its minimum. This is exactly like this. Mathematically, in an abstract sense, this is exactly equal to this. Given a function, find its minimum. But what are the more extra complication? Now the function f, this is called the energy functional. Okay. So f is a function on the class of functions. So functions on the class of functions. So which is infinite dimension, which forms an infinite, usually it will form an infinite dimensional vector space, and even more than that. And therefore you have so many. So basically you have the same theoretical, formulation, that you're minimizing a function, but instead of doing it over a real line, over a plane, over the space or Rn, you're doing it in infinite dimension. This is the complication. Okay, and moreover, U has to be some constraint, and U belongs to a suitable class of functions. So, for example, the first example we saw, finding geodesics, there the U was a curve starting at this point A alpha and ending at B beta. That is the class here. So depending on the problem, your class of functions will change and your L will change, but this is the formulation. So this is a very rough formulation. You can write it in higher dimensions, where you're in higher dimensions. This is replaced with the gradient or the derivative, and so on. So here we have a class of functions defined on the defined on some infinite dimensional space. Okay, so how does one find out the minimum? So the question is, it boils down to finding a minimum to this problem. Okay, so very quickly recall what we have in the finite dimension. In the finite dimension, to find the minimum, so we can do the derivative test, right? We can take the derivative, and wherever the derivative vanishes, that can be a possible candidate for a minimum, right? So here also we can do the derivative of this function. So this is, at this point, this is very vague, but please believe me that you can do it in a very, very rigorous way. You can differentiate to search for minima or minimizers. One can start with first look at derivatives. So the same principle. So I'll write the notation directly. D of f. Okay, this is a derivative at the point u. The point is now a function. So that is the abstraction. The derivative of the functional of the energy capital F. So the Euler-Lagrange equation is nothing but this fact. The Euler-Lagrange equation is that at the point of minima, the derivative, we all know, vanishes, right? So, so this is the Euler-Lagrange equation. So to find the minimum, we can look at the function, we can calculate its derivative, and at the point of, if at a particular point, a point near is a function, remember it's infinite dimensional space, then that can be a possible candidate. Okay, so this is called the variational, these are called the variational techniques, variational methods. And here, furthermore, you'll have some extra constraint that U is in some set, right? So U is not, line field. You cannot be all the things. There is some constraint. So U, as I said, U belongs to some suitable class of function. So U belongs to some function set, okay? Function class, so to say. So this is the Euler-Lagrange equation. So, so now this is kind of this first step, okay? And this is also called the first variation. Now it'll be very quick and kind of very vague. So please feel free to ask questions later on. So this is called the first variation, and this could have been so one of the motivation for calling this subject calculus as variation. So a first variation means that you kind of look at this function f. So how do you calculate? So you can basically calculate the derivative. This is again not exactly right. Maybe I'll write like this. The way to calculate the derivative now, I can tell you, is by the same limiting definition, that limit t goes to 0, f of u plus tv minus f of u. So remember, we're calculating the derivative at the point u, and then we move along the direction v. So you can think of as a directional derivative in when you learn multivariable calculus. So this derivative on v. So you see that I've written the notation for like an inner product, and this is an inner product, but in an infinite dimensional space. So this is a very rough way to write this the derivative, and it vanishes means that this inner product is 0 for any choice of v. Okay, so this is the first variation. Now, the first variation only tells us that this is a derivative. The derivative is 0. But at the point of maxima also it can be 0. At the saddle point also it can be 0. But how does one guarantee? So usually one can plug the value and see immediately that it's a minimum. But also one does the second derivative test, right? So the second derivative test to check if the critical point, so critical point means point such that where the derivative vanishes, is minima or maxima or a saddle point, min, max, or saddle point. One does the similar kind of second derivative test, but now in infinite dimension. Okay, so this is called the second variation formula. Like the first variation, or this is called the second variation, and this has a big history. You have the Jacob equation, you have this conjugate points, and so on. And this is very, very, very important. I'll not go into too much detail, but roughly you look at the second variation. So remember, at the point of minima, so suppose this is the curve and this is the minima point, the second derivative, the function looks like a convex function, right? The second derivative is positive, is not negative. So what it tells you that you move a little bit along the curve, you move above, but because of the slope, you kind of, to leave it as it is, you kind of you slide back to this particular point x, right? And the opposite happens at the point of maxima, that the point of maxima, so that if you move a little bit away from that point, you slide down, you move away from it. So therefore, this is where the the second derivative is less than equal to 0, and it looks like it doesn't look like okay. The interior point looks like a convex path, and the saddle point means that you can find directions along which it is increasing also, and it's along which is decreasing. So maybe I'll give what I have. I will, yes, I should mention one particular example, and then I will stop. Okay. So before that, let me give you couple of examples of the Euler-Lagrange equations for the examples we have seen so far. I've given you so far. So Lagrange equations for the geodesic problem. This problem. This is given by, remember, gamma is the curve. So this exactly tells you that second derivative of gamma should be 0. Okay. So from the physical viewpoint, it tells you that along the geodesic, the acceleration should be 0. This is kind of physically and intuitively, it's hinting towards that. But once you know that the second derivative, so this is a second order differential equation. So what I get is that from Euler-Lagrange equations usually will gives differential equations. And to solve this differential equations is the same as solving this Euler-Lagrange equation, or to find that particular minima or critical points. So here the differential equation is a very simple second order differential equation, that the second derivative is equal to 0 and the solution is x plus b, and therefore you get the straight line. Now you can see the mathematical reasoning why straight line must be geodesic. But this fact carries over to more complicated shapes on the surface or on a Riemannian manifold, but the geodesic is still given by curves whose accelerations are 0. Okay, so I will give one last example and then I will stop. So this is called this was the very classical, and this made this subject very famous in 17th century. So the Brachistochrone problem. The Brachistochrone problem of Bernoulli's. Okay, so this was posed and solved by Bernoulli's, Euler-Bernoulli. So it says that find the, again, so given 2 points, P and Q, and find the curve joining these points such that a particle, I'm drawing it very badly, find a curve joining these 2 points such that a particle which is traveling from P to Q takes the minimum possible time. Again, like the same as we have formulated, but now remember, it's not a free particle. It's like the particle is moving under there's influence of gravity. Okay, so therefore you don't get straight lines. So find the path or the curve, okay, that minimizes the time taken to travel between P and Q only under the influence of gravity. Okay, and variationally we can set it up as problem of minimizing gamma, and then something like, if you start at the point 0, so suppose this is 0, 0, So 0 to b, square root of 1 plus gamma prime square by 2g, g comes from the gravity, dx. And with the constraint that gamma 0 is equal to 0 and gamma b is equal to some beta and gamma is always positive. And I'll just mention the Euler-Lagrange equation. The Euler-Lagrange equation is then given by again a differential equation, which looks like 2 gamma times the second derivative plus the first derivative squared plus 1 equal to 0. Second order, now non-linear differential equation. Okay, and so the differential equations and the theory of calculus of variation are very closely related. The major application of the subject is differential equations, but in higher dimensions you get partial differential equations. And one way to solve some class of partial differential equations is by calculus of variation. And here the answer to this is the famous curve cycloid. So which likes this. So which is, if you take a wheel and you take a point on the wheel, so as the wheel moves like this point will trace this particular curve. Okay, so how much time do I have, or should I stop now?
Teacher, so this is our question hour session.
Okay, so I will stop.
So I think students are enjoying very much.
Okay.
Very nice lecture. So there are two questions in our chat box.
Yes.
First question by Bishoy Majumdar.
Yes.
They said, why the term G within a bracket G and gamma X come here in the in the equation of length of the curve L within a bracket gamma?
Yes. So I see where it comes. I think from here. Okay. So because G is a function of both X and Y. So G is a function of X and Y. So if the gamma is traveling at a point, the curve is traveling at a point X comma gamma X. So for Y, I am putting this. Oh. So it influences that particular point. So this is the density function.
And next question is, what is the density function G in the geometric optics?
So density function G is basically telling you that if the G was 1, one way to understand these things is to take the simplest case. If G was 1, that means it tells you that the medium is non-homogeneous, right? It differs from point to point. If there is air, the property of the air, the physical property of the air tells that at some point it will move at this particular speed, at some point it will move at that particular speed. Mathematically, you just write it as a function, forget about it. So this density function tells you that this is not this is an inhomogeneous medium.
So, okay. So I can give you one suggestion to you.
Yes.
So it is a nice lecture, but in the light of pure mathematics, when you introduce geodesic, so you must mention the surface must be regular and the curves are differentiable curves. So in
no,
so that will be free from all ambiguities.
No. Here it was very less rigorous. We don't want to be rigorous because there are many complications. But this is thank you for pointing this out, because this is one of the major.
Because one can question you that if you consider just a surface of two planes where intersects.
Yes.
So if you take 2 points, then you take a curve mod like y equal to mod x like curve. Yes. So this will be the geodesic. So you cannot find in this definition by geodesic.
Exactly.
You must mention the curve surface must be regular and the curves we consider it that it must be differentiable. So this is the one. I just So thank you very much. Okay.
No, thank you, Dr. Bandopadhyay. Now I request Dr. Nando Das, Associate Professor of Department of Mathematics, to introduce our second speaker, Professor Malay Banerjee.
Thank you, Dr. Shaha. Good evening to all. I am happy to introduce our second speaker, Dr. Malay Banerjee, who is the professor in the Department of Mathematics and Statistics, IIT Kanpur. His research interest is on nonlinear dynamics, mathematical ecology, and epidemiology. He is an experienced speaker in this field. Professor Banerjee completed PhD from University of Kolkata in Applied Mathematics under the guidance of Professor C.G. Chakraborty. Before joining IIT Kanpur, he served Presidency College, Kolkata, and Scottish Church College, Kolkata. Professor Banerjee published more than 175 research articles in the international journal. He has acted as an associate editor in several international journals like Applied Mathematics and Computation, International Journal of Bifurcation and Chaos, Mathematical Modeling of Natural Phenomena. Not only this, he acted as an editor of Ecological Complexity, Theoretical and Mathematical Ecology section of the journal in Mathematics. In present situation, the researchers are giving their full effort to find the solutions to the problem on COVID-19 virus. Today, Professor Banerjee will give us an informative talk on COVID-19 building multi-compartment epidemic model. So I request Professor Banerjee to deliver his talk. Professor Banerjee.
Thank you very much, Dr. Nando, and particularly Nandoda, for your kind invitation and introduction. So first, let me share my screen. Can you see my screen?
Yes, yes.
Okay. So thank you very much for your kind invitation and also kind introduction, and give me the opportunity to talk about our work. But I have to keep in mind that mainly I'm addressing an undergraduate audience. So what I'll do, I'll try to keep my talk at the basic level, such that most of the participants can understand that what we are trying to do here. So in this talk, I'll talk about a couple of issues. That means mathematical modeling of COVID epidemic and also vaccination strategy. And then I will not talk about COVID cases in India from mathematical modeling perspective, but I'll give you some idea that why it is quite challenging to construct a model for a largely populated country like India. And at the end, for interested participants, I'll provide some relevant references. Okay, so for more than 1.5 years, all of us are familiar with all these pictures and also the terminology which are listed in the left column. Now, in case of epidemic diseases and this kind of horrible pandemic, that means once epidemic has a passport, that means the disease can transmit from one country to other country. So those kind of epidemics are known as pandemic. And most important fact is that in daily newspaper, in different news channel, in different discussion, we see several kinds of graphs, different kinds of data, so many information. And on the other hand, mathematics always proceed with a step-by-step logical development. So in order to construct a mathematical model, first of all, we have to understand the nature of disease propagation, complexity of the data, and also we have to realize what are the different inherent information those are hidden within the data, those are published so far. So let us start with a very simple example. And I'm extremely sorry that my slides or this data are not up to date, because I did not get enough time to update the data. But it is up to a reasonable time frame, that is up to the middle of July 2021. So this graph actually shows the data collected from Worldometer, which represents daily number of infected across the globe. And some kind of pattern you can understand here, or you can visualize, and it shows one kind of peak seems to be a peak around this region and another peak at this particular region. But if you look at the corresponding dates, so this peak you can see towards the end of 2020, that is December 2020, and at the beginning of January 2021. And again, you can see one more peak that is around April, May 2021. But from news and different sources, we know that by this time we did not heard about first and second wave. Rather, first wave of COVID that we have observed in the beginning of 2020, that means up to June or July 2020, and second wave from end of 2020 to first 3-4 months of 2021. And this is why we need to think about that when we are talking about first wave or second wave, then what is the population, what is the landscape, what is the country, what is the measure of the different components, those are much important. Before going to that part, let me show you one more picture. This is the daily death data for the entire world up to the same date, that means 18th of July 2021. And if you just compare the previous picture with this one, then you can understand that, okay, the time during which we have observed maximum number of cases during these two time frame, here we can see similar kind of peaks for daily death data. So preliminary assumption is that, okay, if the number of cases increases, there is a chance or possibility in the increase in number of death. But we have to understand what are the reasons of death, whether this is natural or somehow we can prevent the number of death. These are very much crucial questions for which we need some sort of answer before constructing a mathematical model. In order to understand this fact, I will show you two more graphs. Here you can see the country-wise cumulative number of infected data. So this green curve corresponds to United States, this dark blue curve corresponds to India, and this brown color curve corresponds to Brazil, and so on. Some other countries are already plotted here. So once we can see just from rough idea that, okay, number of cases in United States is much higher compared to the states like Iran, Spain, etc. So then we don't need to worry about the epidemic spread in Spain, Russia, etc. But practically we have to keep in mind at the same time, it is known to all of you, but just to remind you once again, that we have to keep in mind what is the total population size of those countries. But what I'm trying to convey through this graph or through this slide, I just wanted to show you that previous two slides shows that, okay, there is a 1-1 correspondence between the number of daily infected and number of daily death. But if you look at the country-wise data for cumulative number of cases and cumulative number of death due to COVID, then you can see these curves are not in the same order. So now you can see that green curve, it is lies above the brown color curve, but the dark blue curve comes below. So what does it mean? That they are not in same proportion for all the countries. If you have a close look, then you can understand there are some sort of alteration in the position of the curves which are lying here. So that means quickly what we can conclude from this simple graph, that number of deaths are not directly proportional to the number of cases with same proportionality constant. Rather, this proportionality constant varies from one country to other country. So this is just as an example, and a simple example, that is what different kind of points and aspects we have to keep in mind before constructing a mathematical model. Now in this slide, you can see the daily reported cases in 4 different countries. This is for US, this one for UK, this one for Brazil, and the last, this one for Germany. This graph clearly shows that maximum number of cases or peak of the epidemic that has arrived at different part of the world at different time point. So what was somehow indicative from the very first graph, that okay, towards the end of 2020 there was a huge number of cases across the globe. Again, during April and May 2021, we have seen similar kind of huge number of cases across the globe. This is true, but we have to keep in mind these numbers are not contributed with equal proportion from all the countries. Rather, there is a large amount of variation in number of cases, their time of appearance, their maximum number of infected on a particular day. These varies significantly from one country to other country. What are the underlying reasons? Underlying reasons are quite complicated. There is not a single reason, but there is a combination of different causes which actually responsible for this kind of variation in number of cases. Those are something towards the disease propagation profile. This is somehow related to the viral strain. This is also related to the human behavior, that means whether they are agreed to follow all the COVID related protocols or not. So many important things are involved. And also from February 2021 and onwards, we have to keep in mind that vaccine comes into the picture. So what I wanted to conclude from these pictures, so this shows the daily number of cases, but so many background phenomena that had taken place in between, like imposition of lockdown, withdrawal of the lockdown restriction, then introduction of vaccine. So many factors are there. Now, in order to construct a mathematical model, the first and foremost question is which type of mathematical model we are going to consider. Depending upon different factors, that means what we are trying to model, which kind of data we have in our hand, how we are intended to apply the model outcome towards the control of the epidemic or some other measure. Depending upon that, we have to consider appropriate modeling setup. So this is a list of different kind of mathematical models that can be constructed for epidemic diseases and even particularly for COVID. But I am not going into any one of these modeling approaches because this needs some sort of advanced knowledge about the mathematics. But in this talk, I restrict myself within the simple setup, that is ordinary differential equation model. Now, once I highlight that I'm going to talk about ordinary differential equation model, some of you might be surprised based upon the fact that what are the basic assumption which is valid for construction of a ordinary differential equation model. So first and foremost assumption for considering ordinary differential equation model is that if I know the current situation accurately, then I will be able to predict the future also accurately. Now the question is that this assumption is true in case of COVID or not. My straightforward answer is this assumption is not true. Then naturally next question arises, then why I am interested to construct this kind of model. This kind of model is just to fit the model outcome with the available data with some sort of variation involved in the differential equation model. So in crude sense, this is not an simple ordinary differential equation model. Rather, it is behavior induced some sort of adaptation of modeling at different time points, which is based upon some setup of ordinary differential equation. What are the meaning of different phrases I have mentioned in this statement? I am going to explain all these things in next couple of slides. Okay, so let me give you a very simple example that, okay, to give you some sort of confidence that yes, ordinary differential equation model can capture some preliminary aspects of epidemiology, and then we will proceed for the formal modeling in case of COVID-19. So this is the simplest model for an infected disease progression, which consists with 3 compartments, that is susceptible, infected, and recovered compartment. The concept is that the assumption here is once infected individuals, they somehow interact with susceptible individual, or they come within the close proximity of the susceptible individual, then the infection is transmitted from infected individual to the susceptible individual. Keep in mind, at this point, we are not concerned about whether it is a viral disease, or it is a bacterial disease, or it is a disease transmitted by some vector or not. Simple assumption that infection transferred from infected individual to susceptible individual once they are coming close to each other. So depending upon the law of mass action or the law of interacting particle over a homogeneous medium, based upon that, this model has been developed. The idea is that once some infected individual comes into close proximity to the susceptible individual, there is a particular rate beta by which infection is transmitted from infected individual to susceptible individual. And then susceptible individuals becomes infected and they join the infected compartment. So that means amount which is subtracted here from the susceptible compartment, that is added to the infected compartment. And here the assumption is that in between, there is no loss in the number. Also, after spending some time within the infected compartment, after certain time period, they will recover, and hence they will leave the infected compartment and join the recovered compartment. So in this case, what we are assuming that this is a model for single epidemic outbreak, number one. Number two, the disease or epidemic is not fatal. So as a result, there is no disease-related death rate. And also the model is considered over a very, very small time frame, such that change in population density or change in number of individuals due to birth or death, that is natural birth and natural death, are not taken into consideration. Now, how this can be ensured? This can be ensured simply if you add these 3 equations, then you can find the time derivative of s plus I plus r is equal to 0. So that means at each time point, sum of these 3 compartments remains constant. So it clearly indicates there is neither any inflow nor any outflow from the total population. And also for the well-definedness of the problem, we have to start with some non-negative initial condition. Now, from this model, 2 important conclusions can be drawn quite quickly. As I have mentioned, that time derivative of this 3 compartment is equal to 0. So that means the sum of st plus it plus rt, this is equal to constant for all time t. And these results also suggest that this time period should not be very large, and it should be within a very small time period compared to the average lifespan of the human individuals, if it is considered as a mathematical model for epidemic diseases within human. And one important aspect that we are always hearing here and there regarding COVID, that is called basic reproduction number. And that is for this model is given by beta n by alpha. So R0 equal to beta n by alpha is the basic reproduction number. What does it mean? It has two interpretations. One, ecological interpretation. Another is spontaneous interpretation from this mathematical model. If you look at this particular term, that is di dt, so you can write this particular term on the right hand side in as a product of two factors. One factor is I, another factor is beta s minus alpha. Now, if you ask yourself that if your initial situation corresponds to total number of individual belongs to susceptible compartment, there is no infected, assumed to be no infected, that means very less number of infected, and as per epidemiological context we can assume there might be only one infected individual, that is the onset of the epidemic. Then the question is, depending upon the transmissibility and depending upon the recovery time, alpha is the inverse measure of average recovery period. So depending upon this and also the size of the population, whether number of infected will grow or it will decline. So that means whether I is an increasing function or I is a decreasing function. So at the initial time point, in a crude sense, we can assume number of infected is 0, number of recovered is 0, total n number of individual belongs to the susceptible compartment. So there is a chance in increase in the number of infected if and only if beta is evaluated at T0, that is beta n minus alpha, this is greater than 0 or less than 0. If beta n minus alpha is greater than 0, then number of infected will increase. And keep in mind that in order to have a positive growth, apart from the positive rate constant, we should have I0 is greater than 0. If your I0 is exactly equal to 0, it will remain there at all future time. That follows from simple theory of ordinary differential equation, because in that case you can write di dt equal to I multiplied with some continuous function of t, and easily you can find out it equal to I0 times exponential some expression of t, and if your I0 equal to 0, so it will remain 0 at all future time. So this is a little bit difference between actual mathematical theory and realistic situation. So for the onset of the epidemic, you need to consider there exists at least one infected individual. But now if you just rearrange the term which ensures the growth in the infected compartment, that is beta n minus alpha greater than 0, from where if you divide both sides by alpha, then you can find out this quantity R0, and this R0 greater than 1 implies beta n minus alpha greater than 0, and which indicates there is a chance of increase in the number of infected individual. And epidemiologically, it means that total number of susceptible is there, that is n. Their average infective period is beta, and 1 by alpha is the measure of the their period of infectivity. So within their infective period, that means the time interval over which they are infectious. So what is the probability that how many individual will get infection from this many population with where the rate of infection is beta, and that is the measure of R0. If this is greater than 1, then it implies there is a chance in for the onset or increase in the number of infected. If this is less than 1, then we can say there is no chance of further growth of the epidemic. As a very simple example, we can consider the influenza data in an English boarding school. The data is taken from a long back, that is 1978. That time and this is the number of days and total number of infected day wise. And from here you can calculate what are the initial number of infected, initial number of susceptible, and for this influenza they have reported that average infective period is roughly equal to 2 days, precisely 2.1 days, and from where we can calculate alpha equal to 1 by 2.1. And then using the basic reproduction number, which can be calculated from the epidemic growth, taking from first couple of days data. During due to the shortage of time period, I'm not going to discuss about how that can be obtained, but if you are interested, you can have a look at the book by Maya Marcheva. It has given the complete details that how beta can be obtained, and from there if you simulate the ordinary differential equation, then you can find that the solution of the problem matches quite well with the number of infected individuals day wise. And this is some sort of approximation, because number of cases or number of infected is given day wise, but differential equation will give you the solution if you are your choice of delta t is quite small. So it can give you the count in terms of second. It will give you a continuous curve. So there might be some sort of irrational number, fractional number. So one can ask the question, what is the meaning of those population size with irrational number? Keep in mind, this is a model. So this is some sort of approximation. So what is our main target? Our main target is that if we set up a model in terms of differential equation, when the parameters are appropriately chosen or estimated, then solution of the differential equation should be a best fitted least square curve corresponding to the data we have in our hand. And that is, we can say, roughly we are satisfied. There might be some sort of disagreement towards the end, and these are related with the asymptotic property. So theory says it will comes down to 0 at infinite time, but practically we know the number of infected in case of common influenza, in case of a finite population size less than 1,000 individual, that should come to an end within a finite number of days. So some sort of disagreement should be there, but depending upon the level of disagreement, we need to consider what is the tolerance level. But what are the take-home messages from this particular model? Take-home message is that if we consider the growth of the 3 compartments, we can see the number of susceptible individuals, those are declining, and ultimately coming to a saturation level. And this level or this value of S indicates that how many individuals they were able to escape from the epidemic. And that is called the final size of the epidemic. On the other hand, this rate curve actually indicates at which rate number of infected individuals are changing day by day. And this particular yellow color curve actually indicates what is the total number of recovery. And ultimately what we can see that number of infected will come to a value 0, number of susceptible will come to a saturated level that will indicate the size of the epidemic, and also number of recovered will be increasing but bounded above, and sum of this number of recovered and number of uninfected, that is final size of the epidemic, that will give you the total population size, because here we don't have any disease related death. Okay, now a reasonable model for influenza like disease that consists with little bit much number of compartment, that is susceptible compartment. L stands for latently infected compartment, and then they are divided into 2 compartments, that is symptomatic and asymptomatic, which is the case of COVID epidemic. And finally, after some time, they are recovered. But here for mathematical modeling, we are not concerned about the fact whether they are treated or untreated, just for simple influenza. So it might happen that some of them, they did not develop any symptom for influenza. because it is assumed that their immune system is strong enough and it can suppress the symptom. But if you go for appropriate testing, then appropriate testing may detect there is a possibility of positive detection of the influenza. And these are the different compartments, as I have already mentioned. And for this, if you consider the model in terms of ordinary differential equation, it looks like this one. But what you can see for this particular model, if you look at the basic reproduction number, so apart from n beta by alpha, you have one more term that is present here. And this is this additional term is contributing to the basic reproduction number based upon the fact that not only infected individual who have prominent symptom, also asymptomatic individual, they can also capable to transmit the disease. That is the most important fact. But if you raise the question whether the susceptible who are getting infection from asymptomatic individuals, they will be ultimately asymptomatic or symptomatic, answer is, how can we ensure that one susceptible individual comes in close proximity of only one infected individual? Rather, in case of huge number of infected individual, if they are available in their surroundings, so there is a chance that one susceptible individual may come in close proximity or close contact with more than one infected individual. And as a result, in the context of COVID, this aspect is very much important, because that will ultimately determine what is the viral load within the infected individual. And what we are considering, that delta is a proportionality constant, its value is lying between 0 and 1, and it determines that a fraction of infection is transmitted from asymptomatic infected to susceptible individual. Also, you can interpret this delta in a different manner, as the delta is less than 1 but greater than 0. So we can consider beta times delta is the resulting infectivity when the infection is transmitted from asymptomatic infected to a susceptible individual. And based upon this particular model, one can calculate this is the basic reproduction number. And again, in this case, we are considering there is no disease-related death rate. But if you assume the disease-related death rate and also demographic term, then you can find some different kind of outcome. So here lambda is the rate of recruitment of the susceptible individuals, and mu is the natural mortality rate. So that means if your time frame is quite large compared to the epidemic outbreak, then we have to consider this kind of parameter into the modeling approach. In case of COVID epidemic, there are couple of thousands of, rather couple of millions of paper already appeared in different scientific journals. Most of them, they have considered demographic term into the modeling approach, but I am not in favor of incorporation of such kind of demographic term into the modeling approach, only for the reason, because if we just try to understand what is the epidemic interpretation of this particular lambda, then you can agree with me probably that this is not a good idea to consider this kind of term in case of COVID. So this lambda actually can be interpreted as this is the rate at which healthy population are recruited in the susceptible compartment. So that means depending upon data over a large time period, if we have a rough idea every year or every influenza like season, on an average how many individuals fall sick, if we have such kind of idea or such kind of data for a long time period and which remains more or less constant at the time of different outbreak, then only we can incorporate such kind of term into our modeling approach. And also, I am sorry to mention that people are interested to incorporate this kind of term into the model just to perform some preliminary mathematical analysis, like the determination of endemic, steady state, and etc. And frankly speaking, in case of COVID, there is no any prominent signal towards the stability or endemicity of the disease. So that's why I follow by the statement that models with demographic terms are suitable for the established epidemic diseases, not for some new epidemic diseases for which we don't know the complete demography of the disease. Now, let me come to the modeling aspect of epidemic. I like this particular modeling approach, but unfortunately for us, we don't have an access to such kind of data. But if you look at their model, it consists with different compartments into the modeling approach: susceptible compartment, exposed compartment, and infectious in the prodromic phase. So that means they will have some sort of possibility to emit the virus particle during their respiratory exercises. And then infected individuals, they are divided into 4 compartments, that is asymptomatic infectious, post-symptomatic infectious, that is asymptomatic, then symptomatic infectious but with mild symptom, and symptomatic infectious with severe symptoms. So they have actually collected the data from a very small region in France, and they have divided the population into these 4 compartments for the infected individuals. Then also for hospitalized compartment, they have divided the entire compartment into 3 different parts. That is severe case who will enter in ICU. If you look at the paper, then you can understand that more precise interpretation is that they were admitted to the hospital directly to ICU. Then ICU, this is the severe case who will enter, that means who were admitted to the hospital but immediately was not put up into the ICU, but there was another compartment of individuals who were admitted to the ICU directly at the time of admission to the hospital. And there is another compartment H, that is severe cases. They need hospitalization, but they avoid to transfer to the intensive care unit. And also there is another recovered compartment and death compartment. And if you look at the flowchart, so flowchart looks like this way. So susceptible individuals, they progress towards the exposed compartment, then IP compartments, and from IP they are transmitted in these 3 compartments, and so on. And as a result, what they have considered it is a very precise modeling approach for a small data set. So that's why death is contributed only from 2 compartments, that is ICU and hospital. So they actually identified there was a possibility, there is a sudden breakup of the immune system, and some of the individuals, they did not give any time to transfer to the ICU, but they suddenly collapsed. So there was 2 routes from where the contribution can go to the death compartment. So in our work, we don't have that much of detailed data or some sort of collaborator from the hospital, but our model was quite similar, quite close to them. What we have considered, there is a susceptible compartment and there was exposed compartments. So that means exposed non-infectious and exposed but infectious. So it can be interpreted as that, okay, some of them, they went for some sort of quarantine or isolation if they travel by air or train or something like that. They went to market, so they are quarantined themselves, so there is no chance of transmitting infection from them. Then the infected compartment is divided into 2 parts, that is symptomatic individual and asymptomatic individual. And then there was quarantined compartment, hospitalized compartment, and recovered compartment. So this is the flowchart how the disease can transmit it. So here what we have assumed, that there is a possibility of death from symptomatic infected compartment and hospitalized compartment. So there are some countries where people were required some sort of hospitalization, but due to limited number of beds, they did not get they was not able to manage hospital beds, and they died from this compartment. But their monitoring system was quite good, and as a result, there was no death from asymptomatically infected compartment. And our model looks like this one. So this is quite complex, and I am not going to show you any detailed mathematical results. But for this model, we have derived all possible aspects. That means what is the maximum number of infected per day, what will be the final size of the epidemic, what is the basic reproduction number, and so on. But what we have done, we have actually estimated all the parameters from the data and also the literature. But most important factor is that we have taken care of lockdown measure. And as a result, the data or parameter values, they are estimated over 3 different intervals. So this is the first 30 days in case of Germany before the lockdown restriction. This is during the first 12 days of the lockdown restriction. And this is the days following the first 12 days of the lockdown restriction. And what is our assumption? Assumption is that the rate of infection was quite high before the enforcement of lockdown restriction. Then it drops down to some intermediate level, and then it comes to a low level of rate of spreading of the infection by mutual contact. But the question is that one can raise the objection that how you are assuming that it will drop from higher level to intermediate level and to lower level. So as a result, we have considered one more possibility that, okay, it was at some high level, then it declines gradually and settle down to some low level of infectivity. And actually from Germany, we got one particular data which gives the effective reproductive number day wise. And from there, we have actually calculated or estimated this beta t that is plotted in blue color. So red color curve is the effective reproduction number. Beta t is the rate of infection that can be calculated from daily number of new infected and also number of infected remains there who did not recover. And from these two data set, that means from red and black color curve, we have estimated this beta t for our model as a blue color curve, and which is a straight line at this level. Then it is a declining line joining this higher value and lower value, and then it comes to this particular level. And you can see, if you have a closed loop, it has a tendency to decline with the advancement of time, because basic reproduction number or effective reproduction number comes down to 1 very slowly. So sometimes they actually fluctuated between some value less than 1 and greater than 1. So for a possible simplified assumption, we can consider it is slowly declining with respect to time. Of course, if you consider some individual based model or stochastic model, this kind of variation can be easily captured. So with this much, what we have obtained with 2 different kind of infectivity, these are the match with the number of total, that means cumulative infected. The left one blue curve corresponds to 3-step beta curve, and this is the continuous beta curve on the right. And if you look at the daily infected data, so red dots corresponds to daily infected raw data, blue color curve corresponds to 3-stage infectivity, and this magenta color curve corresponds to the infectivity which was high at some initial time, then it declines slowly and then retain at a lower value for the rest of the time period. And then we have checked with this model with the data from other countries, and what we have observed that cumulative number of infected and also daily number of infected, they remains within the 95% confidence interval. And this is the plot for Germany, then it is Italy, then it is Spain, and finally this is UK. Now, the next part was we were interested to understand what can happen if the lockdown restrictions are withdrawn. So our assumption was if lockdown restrictions were withdrawn, then some people, they will not follow the COVID protocol appropriately, and then there might be a chance in increase in the number of cases further. And what we have observed, I'm not going to show you the model. The model is quite complicated, consisting with 13 coupled nonlinear ordinary differential equation. But what we have considered that what will be the different proportionate of individuals into compartment, and that can lead to the situation that basic reproduction number less than 1. And in this picture, you can see that if we assume that 10% of the individuals, they are not following the restriction, so there is a clear-cut indication of slow growth in the number of infected individuals when lockdown restrictions are withdrawn. These are with respect to 2020, not 21. So immediately after the first outbreak. Secondly, if we consider that 20% of the individuals, they are not following the protocol, so then you can see there is a rapid growth in the number of infected, and which we have estimated depending upon the level of different basic reproduction number, because less than 1 does not make any sense. It may be 0.9, maybe 0.8, maybe 0.6, and so on. So depending upon that, what we have predicted at that time in a gross sense, not in a country specific sense, that if 20 to 25% people don't follow the COVID related protocol appropriately, so there might be a chance that the height of the second wave should be 4 to 7 times larger compared to the first wave. And then when we have some data, then we have matched our model outcome with the realistic data, and this is the matching with the data from Spain, where you can see this is on the growing mode during the second wave, and this is the matching with the data from Israel, where you can see the number of cases in increase is not monotonic, rather there was a increase at the first time for a certain time period, then there is a decline, and again there is a rapid growth in the number of cases. So in that sense, this model is good enough to match with the data, but never we have used this model for any prediction purpose, because for prediction for COVID, so far as our knowledge goes, we can make beyond that. So now we come to talk about little bit about the vaccination. So in case of vaccination, what we have assumed that vaccines, those are not available at a time depending upon the what is the total number of vaccines required to prevent the further progression of the disease. So that's why what we have considered that after certain time interval, for simplicity of mathematical model, certain number of vaccine will be available. So just as a simple mathematical setup, what we have considered, after every 7 days, we will have 1 million vaccines available. Then question is, in which proportionate we have to distribute this vaccine into 2 groups. One group corresponds to super spreader, that means who are not following the COVID related protocol, and other who are not belonging to super spreader. So that means if we follow the COVID related protocol, so there is a lower chance of getting infection. And depending upon this model and depending upon the distribution in proportion, the number of infected individual and susceptible individual into compartment, what we have observed that if 10% individuals are not following the COVID protocol, then total number of vaccine required to control the epidemic within a finite time period is less compared to the situation if 20% of the people are not following the protocol, and again it is much higher number of requirement for the vaccine if 30% people are not following the COVID related protocol. So this is some sort of mathematical understanding. I am not going into the details, but it means that this is the number of vaccine required for the people who are following the protocol, and this is the required number of vaccine who are not following the protocol. This is the K value on the vertical axis. So K into N is the 10% of the population on this axis, and this is the 90% population of this axis. And these 2 points, that means this length actually determines what is the optimal number of vaccine required in order to ensure that basic reproduction number will be less than 1. But the question is that as vaccine is not available at a time, then whether there is a chance in growth in the number of cases or not. So we have designed the optimal strategy in a particular way, of course, in a non-conventional way, such that if there is an outbreak, the maximum number of infected should be minimum. And these are different kind of control strategies. And for each of different collection of points, this corresponds to how the vaccine are distributed among 2 groups. So for example, in this case, you can understand that number of vaccine given in the first compartment is much larger compared to the number of vaccine administered into the second compartment. Whereas this green point corresponds that more or less same number of vaccine is distributed into 2 groups. And as a result, what you can see that if we follow this particular path, which consists with red dot, then maximum number of infected is lowest 1. So this black dotted curve, it corresponds to the conventional vaccination strategy. So that means without looking at who are super spreader and who not, if we proceed in that manner, then number of infected will be much larger if there is a chance in the growth of the epidemic. Now you can, you might be confused that this black color curve is not much higher compared to this green color curve, but I should explain that scaling of black color curve is given on the right hand panel, whereas for all other curve, scaling are given on the left hand panel. So if we follow the conventional approach, then what is predicted here, of course, for a finite size of the population, that not for a large country, that maximum number of daily infected will be 2,500. But if we follow this optimal path, then maximum number of infected will be below 200. And if I recall correctly, this value was 177 maximum number of infected. Okay. Now, in case of India, according to my opinion, constructing a single model for epidemic disease progression for entire country is not a good choice, because if you look at the data from different states during the first outbreak, it shows different kind of growth profile. This is the first outbreak growth in Maharashtra, and this is the growth profile in all 6 nearby states, which actually share some part of the common boundary with Maharashtra. So these are the states like Madhya Pradesh, Chhattisgarh, Gujarat, Goa, etc. So these 6 states, and it shows a completely different rate of disease progression. Also, total population size in these states are completely different, and hence we have a complete different profile. And what we have considered here, the similar 2-group modeling approach is considered. And then what we have reported that after the lockdown restrictions are withdrawn, then without testing, if huge number of individual move from one state to other state without proper screening, so there is a chance in huge growth in the number of cases in during the second wave if it appears. And this is the fitting of daily infected data with the model outcome. This is the cumulative number of infected, and this is similar kind of matching for all nearby states. And then what is the fact that we are assuming some proportion of population, they are traveling from nearby states to Maharashtra and vice versa. And as a result, if some infected individual, proportion of infected individual who are without testing traveling from one state to other state, So then it shows a clear-cut indication, a huge or quick growth in during the second wave, and that is actually observed in case of Maharashtra. But I am not claiming in this case that this is the only possible reason, but this might be one possible aspect, and that can be captured from the mathematical modeling approaches. So in conclusion, what is the best suitable modeling approach for India? My suggestion would be, if we can construct a model for all the states, and from those states, if we collect the prediction or outcome or simulation result for each of the states, and then consider the total population of India as a whole, then only we can have more or less some reasonable estimate of the number of infected, because the virulence of the disease, the force of infection, the rate of spread of the epidemic spread varies significantly from one state to other state. So if we consider a single model over an entire country for a largely populated country like India, then we might be missing several information. And also a simple factor is that the medical facility, the testing facility, then other requirement is varying from one state to other state significantly. And that's why a multi-scale model will be a good choice. And this also shows some kind of non-transparent reporting of the data. And if you look at the disease propagation or number of infected in Delhi, so it seems to you, while in India during this time period we have observed second wave, if we consider wave as a number of wave as a number of maximum, so then we can consider in case of Delhi, it might be third wave in Delhi, while we have observed second wave in India. And also there is a huge mismatch in the number of Delhi tested, and also depending upon the requirement of the testing. So in case of Delhi, you can see the number of testing can be approximated by a 7 days average to smooth the data set. But what you can observe that they are not at par corresponding to the disease progression profile. This blue curve corresponds to number of Delhi infected, and red color curve corresponds to Delhi tested, and they are mapped or they are presented over a same time scale, but their actual measure is given in two different time scale. And if you look at the same thing for India, so during the second wave, you can see that once there is a high rate of growth in the daily number of infected, by that time there was a significant decline in number of testing. And that's why we don't know what is the contingent amount of infection or what are the unreported cases or underreported cases that we have in case of India. That is also a great challenge to construct a reasonable model for epidemic disease progression in India. Let me stop at this particular point, and these are some of our other works where we have considered some sort of immune response and also some other aspect into the disease progression. Just for your information, if you are interested, you can have a look at it. These are some standard references for these two books, and this is very pertinent in the context of epidemiology, because they talked about human behavior and their interplay to for the spread of infectious diseases. This is a classical book to have a fast reading for epidemiological modeling in terms of mathematics, simple mathematics. And these are the data sources from where we have collected the data. And these are two nice articles. I like them very much. And the title of this literature is quite interesting. And finally, I must acknowledge this person, Vitaly Polpat, who actually dragged me to work in the area of epidemiology from the beginning of COVID-19. Earlier, I was not involved or not much interested in epidemic modeling, but somehow he dragged me in this particular field. And whatever I talked about today, these are carried out with these students and colleagues and collaborators, and the works which I have just shown and did not present it to you those are done with these people from different parts of the globe. Thank you very much.
Thank you, Professor Banerjee, for your nice and informative talk. I think the participants are enjoyed this informative talk. Now, this is the question and answer session, and in the question and answer part, there are two questions from our 5th sem students, Shuikat Majumdar and Runu Haldar.
Yeah, how can one justify a mathematical model with real life data? I think you have posted this data much earlier than I show the means outcome of the mathematical model with the realistic data. Probably towards the end of my talk, I have already shown you that how daily number of infected, cumulative number of infected, that can be matched with the real data and also numerical simulation of the mathematical model. And if you are interested, you can have a look at the book by Maya Marcheva. They have shown that depending upon the data, you have to choose the model. Just for a simple example, in case of COVID, what I have talked about, that is only daily number of infected. But if you have age-specific data, then this kind of model will not work. But in order to match the data with mathematical model, you have to consider age structure model for your matching with the real data. Then second question from Runu Haldar, real life data are discrete, but model is continuous. So how can we simulate? As I have mentioned that against the discrete data set, if your model is continuous outcome, that should be in some sense nonlinear least square curve fitted with the real data. If there is much variation, there are some mathematical technique, and also those are available for how to handle the time series data. You can actually eradicate different kind of noise those are involved with the data in order to match with the model outcome. And also there is another possible answer to your question. If you are truly interested to match with the discrete data, then it is possible to construct a discrete in time and discrete in number kind of model, which is called difference equation model. But in case of large populated country, even for infected individual, daily number of infected individual, even if you look at the worldometer data, they are always talking about 7 days moving average. So 7 days moving average is somehow smoothing of the scattered data which you have different discrete time point. But what I can say that simply this continuous time model outcome should be a least square nonlinear fitted curve with the discrete data set. There is one more chat I can see here. Maybe. Oh no, that is actually from the organizers. Yeah, okay.
So thank you, Professor Banerjee, again for your nice and valuable lecture and to give us a valuable time.
Yeah. Thank you very much for your time.
Okay. So there is a notification for all participants. All the participants are requested to fill the feedback form already posted in the chat box. Now, this is the declaration of the vote of thanks. On behalf of the Department of Mathematics, I am very grateful to our principal, Dr. Subhashish Datta, and IQAC coordinator, Professor Chandra Dasgupta, as well as all members of this IQAC team for their continuous support, without which we cannot arrange this webinar. I like to thank both the speakers for their valuable speech in this webinar organized by the Department of Mathematics along with IQAC Maulana Azad College. I also thank to all the participants, students, research scholars, and faculties for attending this webinar. I also thank all the office staff for their support. Finally, I thank a lot and wishing your good health I declare the end of this webinar.